Alright, so in our first example, we're going to take a look at a beam with simple supports and a distributed load acting on it across the length of the beam. So I hope you don't find this example too bad, and looking forward to calculating deflection in the center, because we know that's where it's going to be the max, right?
Alright, so let's take a look at example 1. We have a distributed load on a simply supported beam. That distributed load is 90.90 pounds per inch, so even our example problems are getting in the spirit of 90s day. So this is the expected deflected shape. We'll go ahead and put in our XY axis, and like we would probably want to start the problem by drawing the shear and moment diagram. So I'm going to ask you guys to pause the video up here and draw the shear and moment diagram for some good practice. Alright, so hopefully this is the shear and moment diagram that you got. We drew the shear and moment diagram just on the previous page when we were looking at the boundary conditions for the simply supported beam with distributed load, so hopefully you're getting a hang of it. This is one of the most common loading conditions we find in structural engineering. Alright, so let's go ahead and look at these boundary conditions. So try to remember what our boundary conditions were, and you can write down a few of the ones that you would want to use. For simply supported beams, I like to first consider the deflection boundary conditions. So I will typically use y of 0 equals 0 because that it means the deflection at A, which is a pin in this case, is 0. And I'll also use the boundary condition y of L equals 0. That means the deflection at B equals 0. Now, if you want to draw the shear and moment diagram in terms of the actual numbers, that's okay. I've left everything here in terms of the variables, and we'll substitute the variables at the end. I find it's a little bit easier just to, as we do the integration, not to keep the numbers around. All right, the other boundary condition that I will use is probably the moment condition. So we find that the moment at the end of the beam and at a pin is 0, so the moment at A is 0, m of 0 equals 0, and m of L equals 0. Now, we created a fourth order differential equation relationship. So if we're going to integrate that back to get the deflection curve, we need at least 4 boundary conditions to help us solve for the constants of integration along the way. Now, we can use other boundary conditions if we choose to. So maybe we want to opt for maybe the shear at 0, v of 0 equal to omega L over 2. We can pick and choose the boundary conditions as long as they're true. We will see that we will need to have at least one deflection boundary condition in order to get the last constant of integration. And depending upon where you are in the integration process, might kind of lead you to which boundary conditions you would want to use to solve for those constants. So I'm going to set up the method of integration here at the bottom of this page. Alright, so to perform the method of integration, we will start from the fourth order relationship, which says that EI y to the fourth equals negative omega, where omega is a constant distributed load. I will integrate both sides of the equation. So that's now going to give me EIY triple prime. And I'm integrating the right-hand side with respect to x, negative omega x, plus my first constant of integration. So we see with method of integration, we're integrating this equation backwards in terms of x, because we're trying to solve for y in terms of x. but we'll also get these constants of integration. Now we have the option right here to solve for C1 directly because we came up with the shear condition. If we remember, EIY triple prime is equal to the shear equation of the beam. So let's go ahead and do that. So let's plug in EIY triple prime of 0. So that's going to equal the shear at 0, which we said in our boundary conditions was omega L over 2. Alright, so if I plug in everything, I have negative omega times 0 plus C1 equals omega L over 2. So now we see that C1, our first constant of integration, has to be a positive omega L over 2. So I can rewrite my equation. EIY triple prime is equal to negative omega x plus omega L over 2. Now, we didn't have to use this condition right away. Remember, we came up with two moment conditions. So we could have solved this at a later point. So maybe you might want to just move on and keep some of your constants of integration. And we'll see that how we do that in a second. All right, let's go ahead and integrate this equation. So if I integrate this equation, I'll move my answer onto the next page. That's going to give us EIY double prime equals, and then we just have to be good at our calculus. So this is going to be just a regular integration of a polynomial, negative omega x squared over 2 plus, now omega L over 2 is a constant, so it's omega L over 2 times x plus C2, which is my new constant of integration. Now I know that the moment at 0, which is EIY double prime of 0, has to equal 0. So let me go ahead and plug in 0. Wherever I see x, I'm plugging in 0. And I know my moment at 0 has to be 0. So I plug in the value of 0 and I see that C2, my constant of integration, also has to be 0. So one of the benefits of calculating some of your constants along the way is that they'll go to 0 and then you can kind of remove them from your math work. Alright, so we got EIY double prime equals negative omega x squared over 2 plus omega L over 2 times x. I integrate both of those. So now I'm down to EIY prime. This is going to equal negative omega x cubed over 6 plus omega L x squared over 4 plus C3, another constant of integration. Now, in terms of my slope, I didn't write any boundary conditions above for my slope. So I'm going to integrate again, and I'm going to have to keep this C3 around. So I'm just going to make a note so that we know you can keep this constant around and be able to solve. All right, so this gives us EIY equals negative omega x to the 4th over 24 plus omega L x cubed over 12 plus C3 times x plus C4. Now I can't just leave it like this. I need to get my constants of integration. If we refer back to our boundary conditions, I had two boundary conditions for my deflection. So using those two boundary conditions, I'll be able to solve for those constants. I want to rewrite my answer in terms of y of x. So this is going to just divide by EI onto the other side. And I get the following answer. Alright, so now I need to plug in my conditions. So I start with the deflection at the pin at A was 0. So y of 0 equals 1 over EI times the first term is 0, second term 0, third term 0. plus C4, and all of that has to be equal to 0 because we had no deflection at A. So therefore, C4 is equal to 0. Now I'll look at the deflection at a distance L. This will be 1 over EI, and now everywhere I see X, I'm plugging in L. So we get negative omega L to the 4th over 24 plus omega L times L cubed over 12 plus C3 times L plus C4, which was 0, so I got rid of C4. The deflection at the roller at B also has to be equal to 0. So now I actually have to solve for C3 and figure out what this is. I swing EI to the other side, so EI will multiply by 0, so it won't really play into my equation. So that's going to give me that C3L equals negative omega L to the 4th over 12 plus omega L to the 4th over 24. So this is going to give me a negative omega L to the 4th over 24. And so I divide by L and I can solve for C3. C3 will be negative omega L cubed over 24. All right, so now I have all my constants of integration. So now I have the equation for the deflection of the beam. The deflection of the beam is going to be that equation y of x. So I plug in y of x equals 1 over EI bracket times negative omega x to the 4th over 24 plus omega L x cubed over 12 minus omega L cubed over 24 times x and that's it. And I'll rearrange things so that it looks a little cleaner. And I'll go ahead and box my final answer. All right, now if we look back at the problem statement, the problem didn't just ask us to solve for the deflection curve. Yes, we wanted the deflection curve, and this will now allow us to predict the deflection at any given point. But it specifically asked for the deflection at midspan. So this is y at L over 2. So I'm just going to plug in everywhere I see x, I'm going to plug in L over 2. And once we got L over 2 substituted for everywhere we see x, we can do some algebra, and then this will yield the following. The result, the deflection at midspan, should be negative 5 omega L to the 4th over 384 EI. And if you're an aspiring structural engineer, go ahead and memorize this formula. Again, this is one of our most common loadings, so knowing the deflection at the midspan is one of the things that you just got to commit to memory at some point. So whether you remember it now or I make you remember it in a future class, go ahead. This could be useful to you, especially if you go into that field of structural engineering. Otherwise, you'll be able to kind of reference some of these common cases and some tables, and that'll be very useful for you in your engineering design career. All right, the question wants a displacement and not just a random formula, so let's go ahead and substitute everything into this negative 5 omega L to the 4th over 384 EI. Very important as we do this that we make sure the units will work out. And that's another reason why I like to keep everything in variable form till the end, because I can make sure my units can check it out. If you didn't keep it in terms of the variables, then you want to make sure you put everything into the same unit system, same magnitude of units, so that as you integrate, some of those numbers that get embedded in there also have units. All right, so I'm going to put everything in terms of kips and inches in this particular problem. So you see I had to convert omega. I plug in my values and I solve for the deflection at the middle of this beam, and I should get that the deflection is negative 0.90 inches. So, as you can see, even our problem answers are getting in the spirit of 90s day, so that we have a deflection of negative 0.9090 inches. The negative sign simply means that it's below the x-axis. Again, this is a calculus type answer.
Now that we finished example problem 1, I hope you're starting to see that beam deflection problems ain't that hard. You just gotta try.